It's not only the Q factor of the loop antenna. There are mysterious effects improving its intermodulation immunity. Sometimes you find an interesting effect you weren't actually looking for. Being passionate about antennas, this is making me curious, and I'd like to invite you joining me on my journey of discoveries. In order to analyze the effects, the antenna must be manufactured to exact dimensions. Check out the precision machined part. Thanks to PCBWay, the sponsor of this video, we can replicate the antenna and make it available to you. Check out the company's website. I'm always finding new, interesting services and products there. Take the easy way with PCBWay. Summarized, we found following facts in previous episodes. A loop antenna is resonating at multiples of its fundamental frequency. We have 3 examples here. A 37-degree delta loop that resonates at all multiples. Measuring a circular loop with matching network, we find only odd multiples. And a planar loop made of white conductors has barely any visible higher resonances. Interestingly, the resonant frequency of the higher modes is somewhat higher than expected. Remarkable, isn't it? We would like to understand the reasons. Perhaps we can take advantage from these effects for further improvements. At fundamental frequency, electrical charge is sloshing back and forth on the loop, similar to water in a bowl. There is an orthogonal mode on the same frequency. We explained it in previous videos, but we won't look at it now. The signal is fed in here via a 50 ohm cable. The integrated matching network transforms the signal voltage up to achieve a good match to the high impedance of the loop. In reality, its impedance depends on the conductor's width. I'm just specifying 1000 ohms to keep it simple. As a conceptual model, we assume the circular loop is a straight conductor corresponding to the circumference of the loop. At fundamental frequency, the charge distribution is oscillating between these 2 states. In reality, the quarter wave transformer is integrated in the loop, but I'm drawing it separately. Due to the short, the field strength is 0 here, and its maximum is at the open end, coupling the signal to the loop. With the 50 ohm cable connected at this point, we are achieving a perfect antenna matching. Now we are increasing to twice the fundamental frequency. Our line transformer is now exactly half a wavelength long and therefore has a null at the open end. So it simply cannot couple that signal to the loop. This explains why the resonance at twice the fundamental frequency doesn't occur. At 3 times the fundamental frequency, we are again getting a maximum at the open end of the transformer, exciting the corresponding resonance. The behavior continues periodically in the frequency domain. Odd multiples of the fundamental frequency are excited, even multiples are not. Okay, the explanation is pretty plausible, isn't it? Now things are getting mysterious. In a planar loop with white conductors, the resonances at twice and 3 times the fundamental frequency are suppressed, contradicting my nice conceptual model. In order to understand what's going on, we need to look at the currents that are moving the charge back and forth. At fundamental frequency, they are directed in common mode. We keep that in mind. The exact current distribution on the band conductor would be difficult to determine, but I can calculate an effective radius based on the wavelength. If this radius were frequency independent, then the higher resonant frequencies would be exactly multiples of the fundamental frequency. In fact, however, we are measuring higher resonant frequencies than expected. So the effective radius of the current at higher resonances is smaller. How can we explain this strange effect? Currents on two conductors are influencing each other through their magnetic field. The so-called proximity effect is causing current displacement too, but don't confuse it with the skin effect. When they are flowing in common mode, the currents are forced outward. When they are flowing in opposite mode, they are forced inward. We remember that the currents on our loop are flowing in common mode at fundamental frequency. This forces them out, causing the effective radius to be larger than expected. I'm illustrating the interaction simplified. At twice the fundamental frequency, two currents are flowing in each direction. And these two interactions are causing an outward displacement, and these two are causing an inward displacement. The effects are partially cancelling out each other, making the effective radius smaller than at fundamental frequency. At 3 times the resonant frequency, we have 6 currents with alternating signs around the circumference. The current displacement effects are almost completely cancelling out. Let me call that radius difference delta. Applied to our conceptual model, we need to shorten the length at higher resonances. However, the length of the transformer remains the same, because the currents on its two lines are always in antiphase regardless of the frequency. As an effect of this, we tend to get a voltage minimum at the open end rather than a maximum. This significantly weakens the resonance. And there we have it. The explanation why the loop antenna made from wide conductors is also suppressing 3 times fundamental frequency resonances. The effective radius can change more on a wider conductor than on a narrow one, causing better intermodulation immunity. Electrodynamics holds fascinating secrets. Perhaps this knowledge could be used for an optimized design, suppressing higher resonances. It's a theory. I don't have a definitive proof, since I can't directly measure the current distribution. However, it's plausible. What do you think? Complicated things are usually not easy to explain. But I'm guessing you enjoyed following my thoughts anyway, if you made it up to here. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.